Hey everyone, this is Candace. So I wanted to make a video for you guys for the pumping lemma for regular languages because I've noticed in the office hours and on Piazza that several of you are having some trouble understanding the basic concepts of the quote game that you play, and I wanted to break it down for you, and then I wanted to so I'm going to walk through Dr. Sullivan's example that she has in the notes for lecture 10. And then I also wanted to do a few examples with you sight unseen because I wanted to give you an idea of what I was thinking while I do these problems. So let's start with her notes. So I want to start off with what exactly the pumping lemma says and what that means. And so that'll give us an idea of what we're trying to achieve as we are doing these pumping lemma problems. So this is what the pumping lemma says. And again, this is the pumping lemma for regular languages. And this is on, again, Dr. Sullivan's lecture 10 notes. I believe this is slide 4. But the pumping lemma just says, if L, which is some language, is regular, then there is, so that backwards E there means there exists, some n that is in the set of integers, positive integers, such that any string W with length greater than n can be written as W equals x, y, z, such that, and there are three things that we need to satisfy here. Number one, y is not the empty string. Number two, the length of substring xy is less than or equal to n. Number three, x, y to some integer k, z is in L. So the reason we call this the pumping lemma is because this right here, this y to the k, allows you to quote pump y some number of times. K should be greater than or equal to 0. It allows you to pump y some number of times and still get a string that is in L. So that's basically the pumping lemma. And what we use the pumping lemma for is we use it to prove by contradiction that strings are not regular. So we take a string that we say, okay, I think this string is regular, but I want to know for sure, and I can prove it by contradiction that it is not regular. Sorry guys, this should actually say that y is not equal to the empty string. So there are some steps that we always need to account for when we're doing these pumping lemma problems, and I will write them on the side for us to keep around because we're going to do several of these, and I'm going to show you I just follow the exact same steps every time. So here are my steps. Alright, number one, you have some language L. And L is the language that you want to prove is irregular, and you want to prove that by contradiction. Okay? Step 2. Now, our pumping lemma says that there is some integer in the set of positive integers. I'm actually going to change that into a p because we generally use the variable p. So we say there is some p in the set of positive integers, and that's what that character means. And I want you to note something right here. So when I say there is some p in the set of positive integers, you don't get to pick that p, okay? You do not get to pick p, okay? So we don't know what that p is. Obviously there are an infinite number of things that p could be. Basically we just know there's some p, so there's some p greater than or equal to 0, and it's an integer. Okay, so what do you get to do? Well, let's go to step 3. Step 3 says there is some string, we'll call it S, that is in L, and such that its length, the length of S, is greater than P. Okay, let me make a note about that. So you do get to pick S, okay? So step 3 is where you get some say in how this pumping lemma goes. And you want to pick a S that's going to work out nicely for you. You may find that some S's that you pick don't work, in which case you need to go back and pick a different S. But you just need one string, S, that is, the original string is in the language L, and that string's length is greater than P. Okay? Now, step 4 says that there is some W is equal to X, Y, and Z such that Y is not the empty string, is not equal to the empty string, and the length of XY is less than or equal to P. Okay? So we're going to split this string up into X, Y, and Z such that Y is not the empty string, and the length of XY is less than or equal to P. And it's important to note here that S equals W. So S equals W equals X, Y, Z. Alright, now you don't get to pick what X, Y, and Z are. Again, and I'm going to write this down. You don't get to pick that, okay? You do not get to pick X, Y, or Z. Alright? So really, all of the work that you have done so far is in step 3, you have decided what the string S is going to be. Now, step 5 is where you get to do some work again. And step 5 basically says you show that there is some K greater than or equal to 0, and I'm sorry for things getting scrunched up here at the bottom, such that X, Y to the K, Z is no longer in the language L. Now you need to pick a K, and then you need to show that that new string, X, Y to the K, Z, is no longer in L. If you can do that, then you have proved by contradiction that this language L is not regular. Why? Because like we just said, the pumping lemma says that a language is regular if it has this property where there are, for all k's greater than or equal to 0, X, Y to the K, Z is always still in L. So if you can prove that there is some K such that X, Y to the K, Z is not in L, then you get to say that you proved by contradiction that the string is not regular. Alright, so let me clean this up a little bit. Alright, so I'm going to leave those steps over there. So this is going to stay here the whole time. Oh, sorry, let me get my pencil back. Okay. So this is going to stay here the whole time. And let's do some problems. So now I'm going to walk you through some of the problems that Dr. Sullivan did in class. The first problem I'm going to walk you through is on slide 5 of lecture 10. And this is what she said on slide 5. So she said she wanted to prove that the language L, which is W such that W has an equal number of A's and B's. She wants to prove by contradiction that this language is not regular. Alright, so step 1, we assume that this language is regular. If this language is regular, then we should be able to do all of these steps over here, and instead of this new string not being an L, it should always be an L. So if we can get a string down here that is not an L, then we have proved by contradiction that L is not regular. So here is our step 1. We go straight to step 2, okay? Step 2 just says there is some P in the set of positive integers here. Now remember, we don't get to pick a P, okay? We need to pick a string. Okay, so this is step 3. We need to pick a string S such that the length of S is greater than P, and S, of course, needs to be in our language. So, you can go through and look, Dr. Sullivan on page 5 of lecture 10, she picked a string first that did not work, and then she picked a string that did work. I'm going to skip straight to the string that does work, but I would recommend going to page 5 of lecture 10 to look at the string that does not work and make sure that you understand why that string does not work. Okay, so we get to pick an S. So we're going to say S equals A to the P, B to the P. Now, we know that this string is, the length is greater than P. It's actually 2P. So that's good. And we know it's an L because it has exactly PAs and PBs. Okay? We don't know what this P is, and that's okay. Alright, so then we go to step 4. Step 4 says that we can split S into some X, Y, and Z. And again, we don't get to pick X, Y, and Z, but we know two things about X, Y, and Z. The first thing we know is that Y is not the empty string. And we also know that the length of xy is less than or equal to p. So this tells us a few things about the composition of x and y here. So from this line right here, we know that x and y are composed of only a's. How do we know that? Well, xy is the beginning of the string, right? They come first. And the length of xy is less than or equal to p. So if the length of xy is less than or equal to p, that means that the most xy could be is only this a to the p. So xy is somewhere in here. It could be all of the a's, if we had p-a's, or it could be some number less than that, because xy is less than or equal to p. So that leaves z being possibly some number of a's, and then all of the b's. So we know that x and y are composed of only a's, and we also know that since y is not equal to the empty string, y has to have at least one a in it. So y has at least one a. Okay? So that's what these two things tell us. Now, we need to go to step 5. Step 5 says that there is some k, and again we get to pick the k, which is greater than or equal to 0, such that x, y to the k, z is no longer in L. Alright, so let's pick a k. Well, this one's pretty easy. Let's pick 0. So if we pick k equals 0, then we're going to have x, y to the 0, z. And let's say that y has, so let's say x has some I number of a's in it, y has some j number of a's in it, and z is going to be equal to whatever's left. So that could be a to the p minus I minus j, b to the p. Okay? So if we're pumping y to 0, then that's just going to be xz, that's going to be xz, and xz is equal to, so I'm just adding these things up over here, a to the I, skip over y, and then z, a to the p minus I minus j, b to the p. Okay? So, what does that leave us with? Let me clean this up a little bit. And hopefully you can see what we're left with. Okay? So what does that leave us with? Well, let's put together like terms here. So we have a to the p minus I minus j plus I. So that's just going to be, give me 1 second. Okay, so we have a to the p minus I minus j here plus a to the I. So that's just going to be a to the p minus j, and then we have b to the p. And we know that this is no longer in L because we said right here y has at least one j, or sorry, at least one a, and that means j is greater than or equal to 1, and so a to the p minus j is always going to be less than p, right? P minus j will always be less than p if j is at least 1, and then we no longer have an equal number of a's and b's. And since we no longer have an equal number of a's and b's after pumping y to 0, then this language is not regular. We have proved this by contradiction. Okay, let's go on to another example that Dr. Sullivan did in her lecture notes. Let me erase this stuff here. There we go, that's pretty good. Alright, so here is example 2. This is on page 7 of the lecture attendance notes. So, this says we have this language, L, which is simply 0 to the n, 1 to the n, such that, oops, not s, n is greater than or equal to 1. And we want to prove that it's not regular. And the way that we prove it's not regular is we're going to prove by contradiction. So we're going to assume that it is regular. And so we're going to say that there is some p in our set of positive integers. And remember, we don't get to pick the p. So p is what's called our pumping length. And we get to pick a string s such that the length of s is greater than p. And again, you want to pick a smart string, one that's going to work for you. And so let's pick string 0 to the p, 1 to the p. Remember, it still needs to be in L, so s equals 0 to the p, 1 to the p is in L, and the length of s is greater than p. We know that because the length of s right now is equal to 2p. Okay? Step 4. So now we're going to split s into x, y, and z. And we don't get to pick x, y, and z, but we know two things about x, y, and z. So the first thing we know is that y is not equal to, I'm sorry, I keep writing that. Y is not equal to the empty string. And the second thing we know is that xy, the length of xy, is greater than or equal to p. So what does that say? What do we know based on that information? Well, let's look. So let's start with xy is greater than or equal, I'm sorry, that should be xy is less than or equal to p. Let me fix that. xy is less than or equal to p. So what do we know about y and x based on that information? Well, let's look at xy is less than or equal to p first. This means that we have xy is it's the beginning of s, right? Because it's xyz, and it has to be less than or equal to p, so it can only be these zeros. It can be all the way up to p zeros, or it can be some number less than p zeros. And then z is going to be whatever is left over. So our xyz here is going to be this. X is going to equal some number of zeros. We're going to call it I. Y is going to equal some other number of zeros. We're going to call it j. And z is going to equal whatever's left over, so p minus I minus j, and then all of the ones, 1 to the p. Okay? So this right here just says that x and y can only be zeros because it can never be greater than the length p. Now, y here is not the empty string. So what do we know about y equals 0 to the j? We're going to put that down here. This means y equals 0 to the j, and j must be greater than or equal to 1 because y is not the empty string. So y is at least 1, 0. Okay, so let's move on to step 5. Step 5 says that we get to pick some k, there is some k, greater than or equal to 0, such that the new string, when we pump y to the k, x, y to the k, z, is not in L. Okay? So let's pick some k. I'm going to pick k equals 0 again. And what that is going to give us is this. So I'm just adding up all the things right here. So we're still going to have, we're going to have x, y to the 0, z, which is just equal x, z. And so what this is going to be, if x equals 0 to the I, and z equals 0 to the p minus I minus j, 1 to the p, then we're just going to have left over 0 to the I, 0 to the p minus I minus j, 1 to the p, and that equals 0 to the p minus j, 1 to the p. And we know, since this j right here is greater than or equal to 1, that these zeros to the p minus j, they're always going to be less zeros than the 1s. So p minus j will always be less than p. And since p minus j is less than p, if you look back up at our original language, we no longer have 0 to the n, 1 to the n, because p minus j can never equal p. It's always going to be less than p. So we have proved by contradiction that this language is not regular. Now, I'm going to skip over the last example that Dr. Sullivan gave you in her notes. I'll let you sort of work through that one by yourself. But here I want to do some examples that are sight unseen. And specifically, of course, I'm going to pull these out of CSC. So I'm looking on CSC, 3rd edition, let's see, page 88. We're looking at 1.29, and I'll write that down. So this is, oops, let me get my pencil back. This is CSC 1.29 on page 88. Now this problem, again, I have not seen any of these problems beforehand. I'm going to work them out without having looked at them before, so that you can get an idea of what I'm thinking, and then if I run into some problem where my logic doesn't work, you can see me sort of rework my logic such that it does work. So this problem has actually 3 problems in it. It has an A, B, and C. The answers for A and C apparently are in the text, and so you can check my work if you'd like to. And then we'll just do B freehand, and you will have to believe that what I did actually works. So let's start with A. Alright, so again, CSC 1.29 on page 88, this is A. And the language we want to prove is irregular is 0 to the n, 1 to the n, 2 to the n, such that n is greater than or equal to 0. Now this looks very much like the problem we just did, and it's going to work very similarly to the problem that we just did. So there is some p in the set of positive integers. We don't get to pick p. However, we can pick an s. There is some s that is in the language L such that s, the length of s, is greater than p. So what s am I going to pick? Well, I hope you've guessed it. I'm going to pick 0 to the p, 1 to the p, 2 to the p. And we know that the length of s is greater than p because it's actually 3p, as you can see. And we know that s is in L because it fits this form. P is equal to p is equal to p. So s is in the language. Now, step 4 says that we can split s into x, y, and z such that there are 2 things that are true about x, y, and z. First of all, y is not equal to the empty string. And second of all, the length of xy is greater than, oh, sorry, it's not greater than, it's less than or equal to p. Okay? So what do these 2 things tell us? Well, if xy is less than or equal to, if the length of xy is less than or equal to p, then we know that in this string, xy can only be some number of zeros, because in order to get to 1 here, the length of xy would have to be greater than p, and it can't be. So x and y are some number of zeros, so we'll say x equals 0 to the I, y equals 0 to the j, and z is going to be everything that's left over, so z is going to equal 0 to the p minus I minus j, 1 to the P, 2 to the P. Okay? And because we know that I is not the empty string, we know that J must be at least 1. So Y must have at least 1 0 in it. Alright, so that's step 4. Let's go on to our final step, number 5. Step 5 says there is some K greater than or equal to 0 such that X, Y to the K, Z is no longer going to be in our language. So let's pick some K. Well, I'm just going to pick 0. It's a nice number to start with. If you ever pick 0 and you realize that at the end of the problem you have not actually proved that X, Y to the K, Z is no longer an L, then you need to pick another number, and I would recommend not picking 1, because if you pick K equals 1, then you're just going to X, Y to the 1, Z, which is equal to X, Y, Z, which is the original string you had, which was an L. So don't ever pick 1, but you know, you can start with 0, and if that doesn't work, move up to 2 and see if that'll work for you. Okay, so I'm going to pick K equals 0. Okay, so that gives us X, Y to the 0, Z, which is just XZ, and that equals 0 to the I. Again, I'm just looking right here and adding these things up. 0 to the P minus I minus J, 1 to the P, 2 to the P. Okay, and that's going to equal 0 to the P minus J, 1 to the P, 2 to the P. Now, what do we know about P minus J? Well, since J is at least 1, then P minus J, P minus J is always going to be less than P. So this new string is not going to be in our language because we no longer fit the form 0 to the n, 1 to the n, 2 to the n. We have this number P minus J that is always less than P, so it's no longer in the language. So we have proved by contradiction that this language, 0 to the n, 1 to the n, 2 to the n, is not regular. Alright, let's do part B. Let me clear this up a little bit. Alright. Problem B is our language equals www such that W is sigma star, where our sigma is AB. So W can be, so our sigma is AB, so W can be anything in that language, so you know, any number of A's followed by any number of B's, or B's followed by A's, you know, as many times as you want, that can be W. Our restraint here is going to be that this W needs to be repeated 3 times. Okay, so let's pick, so first of all, step 2 says there is some P in our positive integers that's going to be our pumping length. We don't get to pick P, so we can just go straight to the next step. There is some S in L such that S is going to be greater, the length of S is going to be greater than P, so we get to pick the S. So you may want to initially say something like S equals A to the P, A to the P, A to the P, but you may notice that this is not going to work because if we start pumping up or down, we have no way of knowing that the number of A's that we have is not divisible by 3 anymore, and so the string that we get after we pump up or down may still be in the language. We can't prove with this string that our new string is not in the language, so we're going to have to pick something different. So let's think about what we could pick. So we could have same sort of idea. If you have A, B, I'll write this out even though it won't work, to the p 3 times, that's also not necessarily going to work because we don't really have any way of saying what exactly x or y is. Remember, we don't get to pick x or y. So that will also not work. Now, here's where I'm going to pick a smart string, and hopefully you will see why this string will actually work out more easily than the other strings, which would not have worked at all. I'm going to pick a to the p, b, a to the p, b, a to the p, b. Okay? So we know that this string is an L because this is W 3 times. And we know that the length of S is greater than P because the length of S is actually equal to 3P plus 3. Okay? So step 4 says that we split that string into x, y, and z. And again, you don't get to pick x, y, and z, but you do get to know two things. Number one is that y is not the empty string. Number two is that the length of xy is always going to be less than or equal to p. So what does that tell us? Well, since the length of xy is always going to be less than or equal to p, then we know that xy can only be up to possibly all of these a's. It can never get to this b, because if it got to this b, the length would be greater than p. So we know that x is some number of a's, we'll call it a to the I. We know that y is some number of a's, we'll call it a to the j. And we know that z is whatever is left over, and that's going to be a to the p minus I minus j, b, a to the p, b, a to the p, b. Okay? And we also know that since y is not the empty string, that this j right here must be greater than or equal to 1. So y has at least one a in it. Now we can go on to step 5. And step 5 says there is some k greater than or equal to 0 such that x, y to the k, z is no longer going to be in our L. So let's pick k equals 0 again. That's going to give us x, y to the 0z, which is equal to xz, which is equal to a to the I, and again I'm just adding up here x and z. So x is a to the I, z is a to the p minus I minus j, b, a to the p, b, a to the p. And that of course equals a to the p minus j, b, a to the p, b, a to the p. Now, you know that since j is greater than or equal to 1, p minus j is always going to be less than p. p minus j is less than p. Okay? So that means we no longer have 3 w's in a row. Okay? If this was our w, then this is not going to be w anymore because this string, a to the p minus j, b, has less a's than this string, and so this can no longer fit in our language. There's no w that we can make up that would somehow make this string fit in our language www. So we have proved by contradiction that this language L is not regular. Let's move on to part C of this problem. Part C says that our L is equal to a to the 2 to the n such that n is greater than or equal to 0. And it gives us a little hint, and it says a to the 2 to the n means that we have some string that has 2 to the n a's. So that means that the string that we are going to end up with is going to have some number of a's that is a power of 2. Okay, so step 2, we don't get to do anything. It just says that there is some p in the positive integers that will be our pumping length, and we get to pick an s. Step 3 is there is some s in L such that s is greater than p. Now we get to pick an s. Now again, I haven't seen this problem before, and so it might take me a little bit of time to figure out what I want to do here. Now you may want to start off by, and I say you may, but this is incorrect thinking. You may want to start off by saying, okay, I'll just say s equals a to the 4. But remember, you do not get to pick p. So you can't just plug in a number here. You need to have something that is in terms of p. You don't get to pick it. Okay? So you can't just say s is a to some power that is a power of 2. So we can't use that. Now, I don't know if this is going to lead me to the right answer, but I know that I need to have p somewhere in my string so that it can take account for the fact that I can't pick a p. And so I'm going to try s equals a to the 2 to the p. And that means that I have 2 to the p number of a's in s. Okay, now this may make you a little bit uncomfortable because you don't know what 2 to the p means exactly, because you don't know what p is, but we know that we do have some number of a's that is a power of 2, because p is a positive integer, and we do know that s is greater than p because since p is a positive integer, for example, if p equals 1, you'd have at least 2 a's. If p were 2, you would have 4 a's, and so on and so forth. You are always going to have some number of a's that is greater than p. Okay, so let's stick with that for now and see if it gets us anywhere. So step 4 is we can split s into x, y, and z such that we don't get to pick x, y, and z, but we do know 2 things about x, y, and z. The first thing we know is that xy is less than or equal to p. The length of xy is less than or equal to p, and we know that y is not equal to the empty string. Okay, so what does that mean about the composition of xy? So obviously, if xy is less than or equal to p, then xy is just going to have some number of a's in it. So x is going to have some number of a's, I'll call it I. Y is going to have some number of a's, I'll call it j. And z is going to be what's left over, so z is going to be a to the 2 to the p minus I minus j. And since y is not equal to the empty string, we know that this j must be at least 1. Okay. So we've gotten through step 4, now we just need to do step 5. So step 5 says that we can pick a k greater than or equal to 0 such that, if we pump x, y to the k, z, so if we pump y at k times, then our new string is not going to be in the language anymore. Okay, so we need to pick this k. So we need to be kind of smart about it because we want to make sure that we end up with something that cannot possibly be a power of 2. Okay, so what do we pick for k? Well, I'm hesitant to pick 0 for k because if we start taking a's out of our original s, a to the 2p, we can't necessarily be sure that our new string is not still going to have some number of a's that is a power of 2. And so I don't feel like k equals 0 is going to be a good idea. This one is going to require a little bit more thought, but I think that as long as we pick a positive k, we should be okay. I don't want to pick a positive k that is a positive power of 2, so like I don't think I want to pick 4. I think that might lead me into some problems, but I'm going to try k equals 2 for right now and see if that works. So k equals 2 would give us x, y to the 2, z, is going to give us x, y, y, z. Now because I don't know what this j is, I just know that some number greater than or equal to 1, I can't say a whole lot about this string, so this string would just give me a to the I, a to the j, a to the j, oops, j, a to the p minus I minus j, and that of course is just going to give me a to the p plus j, and I'm not sure if this will necessarily sorry, this should be a to the 2p. So this will be a to the 2p plus j. And I'm not necessarily sure that this plus j here isn't going to get us into trouble. So let me think about this a different way. So we know that y, the length of y, is greater than 0. And the one thing that we want to worry about is what happens if we get to a to the 2 to the p plus 1, because that would be our next power of 2. And the way that we could get to a to the 2p plus 1, a to the 2 to the p plus 1, is if we have a to the 2 to the p plus a to the 2 to the p, then you would be basically multiplying a to the 2 to the p times 2, and that's going to give you a to the 2 to the p plus 1, that's just a power of 2. And so we just need to prove that y is not this. So the length of y is not 2 to the p. Because as long as the length of y, is less than 2 to the p, then we will know that our new string does not fit this form up here. Okay, so what is our length of y? Well, when we were looking at splitting up a to the 2 to the p into x, y, z earlier, we knew that x, y had to be less than or equal to p. Okay, so if x, y is less than or equal to p, then what does that mean about a to the 2 to the p? Well, let's just plug in some numbers. So again, like I said, if p equals 1, then we have 2 a's. If p equals 2, we have 4 a's. If p equals 3, we have 8 a's. If p equals 4, we have 16 a's. So at most, y, the length of y, could only ever be 1/2 the length of s. So if p equals 1, like I said, we would have 2 a's. So y could only be 1p because y has to be less than or equal to p. So at most, y can only be equal to 1/2 the length of s. And it goes down from there, right? So the actual length of y is log base 2 of the length of s. And so if we add these together, if we have xyz, which we know equals the length of s, and then we want to add the length of y, which is equal to the length of log base 2, the length of s, then I'm on to something here. I'm pretty excited. I'm going to erase some of this stuff just to make myself some more room. So if we have xyz equals s plus the length of y equals log base 2 of s, then we end up with the length of xyz plus the length of y is at most, so it's always going to be less than or equal to the length of s plus log base 2 of the length of s, and that is always going to be less than 2 to the p plus 1. Because log base 2 of s is never going to be the length of s, so we'll never actually get to s plus s, which means we'll never get to 2 to the p plus 1. So this right here, x y to the 2z, or x y y z, is always going to have some length that is not a power of 2, and if you're confused about that, I'll write it out for you here. So our original string xyz, the length was 2 to the p. xyz obviously is going to have a length greater than that. Specifically, it's going to have a length that is at most s plus log base 2 of s, and this is always going to be less than the length of 2 to the p plus 1, which is our next biggest power of 2. And so since it's not this power of 2, xyz is not this power of 2, and it's not this power of 2, it's in the middle, it cannot be a power of 2. So this, not a power of 2. And so it cannot be, so x, y, y, z is no longer in our L, which means that this language L is not regular. Alright, so I hope that that helped you out a little bit. Please don't worry about part C there. I don't think that Dr. Sullivan will ever give you anything really that hard, but I hope that seeing me think through a few problems helps you in figuring out how to do the pumping lemma problems on your homework.